So it's a great honor to have Noga Alon on our big seminar. He's he doesn't really need any introduction. Simply one of the biggest combinatorialists that we have, and he will talk about fair partitions today. And welcome, Noga.
Okay, thank you, Andre. Thank you all for participating. I'm impressed to see that so many people know the decimal expansion of pi. So you could really enter this meeting. So I'll talk about fair partitions, and let me start by explaining what I mean by this. So I'll give many examples. And I should say that there are many other examples that I'll not mention, but still I think that those are interesting. And incidentally, I'm not sure if I see the probably if you have questions, then just unmute yourself and ask a question, because I'm not sure if I can see the chat here. Probably I cannot.
In case somebody writes in the chat, I can say it out loud.
Okay, okay, good. So probably the first example historically of what I mean by partition problems or fair partition problems is the Ham-Sandwich Theorem. So this one was posed by Steinhaus and solved by Banach by reducing it to the Borsuk-Ulam theorem. And it says that for every n nice measures in Rn, so let's say absolutely continuous with respect to the Lebesgue measure, or it's enough to assume that the measure of any hyperplane is 0, then there is a hyperplane which bisects all the measures, right? So you see here an example in dimension 2 is a blue measure and the red measure. And as I said, this was posed by Steinhaus, proved by Banach. There is a famous quote of Steinhaus that he said that his greatest mathematical discovery was the discovery of Banach. And supposedly this is because Banach was able to solve many of his questions, and maybe this one was one of the examples. And it's clear what is fair here, right? So the partition is fair according to each of those measures. Okay, this is one example. Here is another one. So this is called the Necklace Theorem. For k equals 2, it is basically implicit in a result of Hobby and Rice in L1 approximation, but in this formulation for k equals 2 was first proved by Goldberg and West, and then we found some shorter proof, and there is a more general statement that is the one that I wrote here. So, what is the statement? We have a necklace, and we open it at the clasp, so just an interval of beads. And suppose that it has k times ai beads of type I for every type I between 1 and n. And I assume for now that the number of beads of each type is divisible by k. And what we want is to partition it to k fair collections. So one way to think about it is that this necklace has been stolen together by a group of k thieves, and they want to partition it fairly among them, and they wanted that each of them will get exactly the same number of bits of each type, and they want to try to minimize the number of cuts. So they want to cut it in a small number of places, and then split the resulting intervals into k collections, so that each collection will contain exactly ai bits of type I for each of the types. Now, if the number of bits of some types are not divisible by k, we don't actually have to assume this. There is some way to use the result for the divisible case and use some integrality theorem for network flow to show that basically in the general case, you can always, with the same number of cuts, ensure that each one will get the number of bits that he gets of each type will be either the floor or the ceiling of the number of bits of this type divided by k. Okay, and we want to cut in a small number of places, and what this statement says is that always it is possible to cut in at most k minus 1 times n places. Now it's easy to see that this is tight for some simple looking necklaces, namely if your necklace is such that the bits of each type are contiguous on the necklace, then just to cut the collection of each type into k non-empty pieces, even if they are not equal, we have to have at least k minus 1 cuts inside this contiguous part corresponding to each of the type of the bits. And since we have n types, then we need k minus 1 times n cuts, at least sometimes. And the theorem says that k minus 1 times n cuts are always enough. Even if the necklace is very, very complicated, we can always do it with k minus 1 times n cuts. Okay, so this is about the second example. Here is another one. This is called the cycle and triangles theorem of Fleischner and Stibitz. So it says that whenever we have a cycle of length 3n, and it is partitioned into n sets of vertices, each of size 3, so you can view it as placing triangles, n triangles on top of the cycle. That's why it's called the cycles in triangles. Then always there is a fair independent set, so an independent set containing exactly one vertex from each triangle. So here in this sense, it is fair, and this version of the problem was a conjecture of Du, Shu, and Huang, and soon after that, Erdős conjectured a more general theorem that, or a stronger result that actually we can partition all the vertices into 3 independent sets with the same property, namely that a graph consisting of a Hamilton cycle like that plus the n triangles has chromatic number 3. And in fact, what Fleischner and Stibitz proved was even stronger than that. Is the least coloring version of that. But here, let me look just at one independent set that is fair again in the sense that it contains exactly its fair share from each of the triangles. We have a few years ago, we found with many co-authors some extension of this. So you see, it's so many co-authors that I'm not first in the alphabetical order. And this is with Aharoni, Berger, Chudnovsky, Kotlar, Lebel, and Ziv. And here is a statement of this more general thing. We have a cycle, and now the length of the cycle is a sum of n odd numbers. So numbers of that I denoted the ith number by 2ri plus 1. So the cycle is partitioned to these disjoint sets of size 2ri plus 1. Then we can find an independent set on the cycle that contains exactly ri vertices of each set Si. Okay, so this, and the triangle's case is, of course, the case where ri equals 1 for every I. So this is here is yet another one. This one is a conjecture, not a theorem, but it's still a statement of the same type. And that's a conjecture of Ryser from the 60s. And he conjectured that every Latin square of odd order n, so a Latin square is just an n by n matrix in which the entries are numbers from 1 up to n, and every row and every column is a permutation of 1 up to n, like the one that you see here. So the conjecture is that if n is odd, then it contains a Latin transversal. What is Latin transversal? It's like the examples that you see here in each of the fixed colors. So it's a set of n entries of the matrix, one in each row, one in each column, and one of each number, right? So, so again, this would be fair in the sense that a Latin transversal is n entries out of the n square. So since every symbol or every number appears n times, then it would be fair to contain each number exactly once. So this is a conjecture. Here, actually, one could wonder about the partition version as well. And here the partition version is not true. So this was observed by Euler for the even case, and was proved by Mann for every n, which is 1 modulo 4. And then by Wanless and Webb and by Evans independently for the remaining values of n. So for every n which is not 1 and 3, there is always an n by n Latin square that cannot be partitioned into Latin transversals. To partition a Latin square into Latin transversals is equivalent to the existence of what is called an orthogonal Latin square to this to the existing Latin square, namely another Latin square that we can put on top of this square, so that every ordered pairs of numbers ij will appear exactly in one place, and this is exactly equivalent to the existence of partition. So a partition is equivalent to say that the Latin square has what is called an orthogonal mate. And indeed, in those in the paper of Wanless and Webb, they call those squares that do not have orthogonal mates bachelor Latin squares. So this is and basically the examples follow from some addition tables of some group, but you have to change it a little bit. So for the even case, you can just take the addition table of the n, and for the more complicated things, you have to do something a little bit more complicated, but that's the result. Still, the conjecture of Ryser may be true, that maybe for every odd n, we always have one Latin transversal. There was a, so I want to state this conjecture in an equivalent form because this will be closer to some of the things I'll discuss later. So here is an equivalent form. Whenever we have a proper edge coloring of the complete bipartite graph KNN by n colors for n odd, there is a perfect matching containing exactly one edge of each color. Indeed, we just think about the left color class as representing rows, the right color class as representing columns, and each color class represents one symbol, and therefore a transversal is a perfect matching because it is one in each row and one in each column, and the fact that it contains all the symbols once is exactly means that it contains exactly one edge of each color, and here you see it in the shaded edges in this picture, right? So we have one red shaded edge and one blue and one yellow. Okay, so I'll repeat myself that whenever there are any questions or comments, don't hesitate to stop me. There was a stronger version of this conjecture. This is it was due to Stein in the 70s. And he thought that maybe you don't even need the original coloring of this complete bipartite graph to be a proper coloring. So the statement was that for every not necessarily proper coloring of the edges of K and N by n colors, where each color appears n times, but now it can appear anywhere, well, there is a matching now, not a perfect matching, because there are some simple counterexamples, but a matching of size n minus 1, containing, again, a fair amount of each color, and the fair would be here at most one edge of each color. So this is what, but this turned out to be false. So life is not always completely fair, and there is a nice counterexample by Pokrovsky and Sudakov, and they found some coloring of the edges of K and N by n colors, so that every color appears exactly n times. It's not a proper coloring, and every matching now, every perfect matching, if you want, or every matching of any size, misses at least some constant log n of the color classes. So you have to miss at least some constant log n color classes, and therefore if the matching is of size n minus 1, then certainly it contains some colors at least twice. Okay. But still it could be, so we said that in this case we cannot ensure something that is completely fair, but maybe we can always ensure something that is roughly fair. And this is actually one of the conjectures we raised in this multi-author paper with Haroni, Berger, Chudnovsky, Kotlar, Lebel, and Ziv. So we think that the following should be true for any edge coloring of K and N, now by any number of colors. So we don't specify the number of colors, and we don't specify the number of edges of each color. So you just color it any way you wish, by any number of colors you wish. And then always there would be a perfect matching that represents the colors nearly fairly. Okay, so what does it mean nearly fairly? If the number of edges of color I in the matching is G sub I, and the total number of edges of color I is F sub I, then the fair amount that the matching should get is fi over n of color I, right? Because the matching is n edges out of n square, so it's a fraction of 1 over n, and therefore if we would have been completely fair, then gi should have been fi over n. Well, we already said that we can't ensure it will be exactly fi over n. In fact, fi over n does not have to be an integer, but the conjecture is that we can always ensure that the difference, each difference, will be at most some constant. And in fact, I think we even conjectured it with the constant being 2. So maybe it's true with a small constant, but and we did prove it for 2 and 3 colors with the constant being 2. So for 2 colors, this is basically trivial. You can try to think about it. It's some continuity. And for 3 colors, it's already some proof. So whenever you color the edges of k and n by 3 colors in any way, then you can find a perfect matching that contains roughly the right amount of each color, and roughly the right amount is up to an error of 2. I should say that if you just take a random matching, then with high probability, it will also represent all the colors reasonably well. Namely, the errors will not be bigger than something like square root n. But the main thing here is that we don't want the error to grow with n. So we want it to be constant, independent of the size of the graph. Okay? And one of the results I'll try to tell you about is a weaker version of this conjecture. So I'll replace the constant, this constant error, by an error that depends on the number of colors, but does not grow with the size of the graph. Okay, and in this weaker formulation, the conjecture holds, and it holds in a much greater generality. So not only for perfect matchings, but for all kinds of other structures, and even to hypergraphs. And I'll try to describe some example of this type. Okay. So this is about the examples, and now I want to talk a little bit about algorithms, but maybe before it, let me pause again and ask if there are any questions, comments.
Are the proofs constructive? The proofs of
so this is exactly what I'll talk about soon, and they are mostly not, but some are. But and this is indeed an interesting topic. So right, so I have a gallery view in the second computer, so I can see at least some of you, and I can see the numbers.
Noga, can I ask you a quick question? So when in this conjecture, what regime would you say is the most interesting? What is the most challenging regime?
Right. So I think an interesting regime is a constant number of colors, but somehow for the proofs we know, the most challenging regime is when the number of colors is very big, and then when it gets close to these things like the conjecture of Stein or Ryser, right? So maybe challenging is when there are many colors. I think it's quite interesting also when there are 10 colors, right? So when the number of colors is just constant. Okay.
Thank you.
Another stupid question. So as for the necklace problem.
All right.
So probably if you just take a random necklace, then it's wonderful, right? Then you can
a random necklace or a random.
yeah, random necklace.
So wonderful in
the sense that you need very few cuts.
Maybe. So I didn't think about it, but it could be. So you expect that you will need less than it might be, right?
Yeah, I think that definitely not this k minus 1 times n is.
Right, yeah. So it might be that because it's random, then maybe we'll have right. I tend to believe it. I don't know offhand, but okay.
Okay, thanks.
But right, but as we said, there are some examples where you need this many, and maybe I should say also that finding the minimum possible number of cuts that you need is a hard computational problem. So it's right, but I agree. I mean, it's that right. It makes sense to believe that that with random and a small number of types, probably you will find one interval that contains exactly what you expect. Okay, so something about the algorithmic aspects. So what I wrote here is that many of the known results on fair representation, and as I said, there are many others that I didn't mention here, but this is kind of a representative collection. So many of the known results are proved either by topological or by algebraic techniques, and those are not constructive. So they provide no efficient procedure for solving the corresponding algorithmic problem. And in fact, it's interesting to find an algorithm, not only if you care about algorithm, so, you know, if these thieves, they have the necklace, they really have to split it. So they have to do it. Their existence is not good enough for them. They want to bring the beads home. But even if you are not interested in the algorithms, kind of constructive solutions, this is sort of checking the need of the topological or algebraic techniques. So we tend to believe that maybe more combinatorial proofs will hopefully or will possibly be more constructive. And here is in particular, so we mentioned the necklace, here I wrote it just for k equals 2. So we know that every open necklace with 2 AI beads of color I for each eye, we can cut them in n places and then get 2 collections, each with at most n plus 1 over 2 intervals, which will contain exactly AI beads of type I. This theorem and the more general extension, they are all proved by applying some Borsuk type fixed point theorems, and maybe I say a little bit more about this, so let me go through it. I'll not say much. So here are the steps of the proofs for general K for this necklace theorem. There are 2 very easy and constructive steps, and then the main one. So the first one is just an easy observation that if you know the statement for a group of K1 thieves and a group of K2 thieves, then you know it for K1 times K2. And this is done just by first splitting the necklace evenly to K1 fair pieces, and then for each of the K1 fair pieces, you put them together and you split them to K2 fair pieces. And if you work out the numbers, then the total number of cuts turned out to be the correct one. Okay, so this is one observation. Then another one is to change it to a continuous problem because we want to apply topology. So we just change the necklace in the obvious way to an interval colored by n colors. We replace each red bit by a small interval colored red, and this will give us some n probability measures if you normalize them. And what we'll try is to cut each of these probability measures in a fair way. And then comes the main part, and this uses some fixed point theorem. In this particular case, it's a result of Baran, Schlossman, and Such, which is basically some extension of Borsuk, and this is used to prove the statement for prime k. Now, somehow the topological argument works only for prime values. In fact, it's not even true for non-prime values because we need some free action of a group. And therefore, the first step, which was an easy observation, was lucky, right? Because it's enough to prove it for the prime case in order to know it for every k. Otherwise, groups of a non-prime number of thieves would have difficulties. Okay, so of course I'm not saying here anything about the actual proof, but because I'm not, then I can give you two links to some YouTube presentations that discuss some aspects of the actual proof, and especially the first one is very professionally made, so you are welcome to watch it.
No, good. Maybe it's a good point. I think Gabor Tardas was commenting on the your discussion with Janos in the chat. Don't you need n times k minus 1 cuts just to have enough degrees of freedom?
Yes. So, but what is what's the question? You mean it relates to the comment about the probabilistic case, or what?
This is my understanding. Maybe Gabor can comment on this.
Yeah, it was about the probabilistic necklace. If you have a lot of bits in every color, then it's kind of a continuous case, and even the random thing would just, it doesn't mean much having random distributions there. I mean, they will.
Is it true? I mean, so somehow my thought was that, for example, if you have just two types of beads and you have a random walk, so random walk passes through the origin in the sense, it means that there is an interval from the beginning that contains exactly the same number of red beads and blue beads. And this is something that you don't expect from a non-random thing. So somehow I'm not sure that even if you don't have enough degrees of, but okay, I'll not, it might be, but I'm just saying that with random thing, my impression is that you could hope to get things that you cannot hope to get in a non-random case. Okay, like for example, in a random thing with 10 types of beads, I would expect that always there would be, I mean, definitely there would always be, if the necklace is very long, there would always be one interval containing exactly one bead of each type. And this is not something that you can expect always, right? It does not exist in those structured things. So this is just to show that in a random thing, you can sometimes expect to find things you cannot find in the general case. Do we agree on this, or it's?
Well, I mean, you mean that, did you convince me? No.
So, okay, so did I convince you about the following? So this is a trivial thing. If you have a long random necklace with 10 types, okay, then always there is an interval which contains this one bit of each of these types, okay? So an interval of length 10 containing exactly one, so this will just exist, right? Namely, if what I want is an interval containing, I mean, this is also a fair thing of some sort, and this is something that exists in a random thing and definitely does not exist in the general case, okay? So maybe it is, so about this, I think you are convinced, right?
This I'm convinced, but in the original problem, if you have like close to infinite many bits, then you need very long intervals, and very long intervals will have no special properties, because then random changes will be enough to distinguish all those long intervals.
Okay, yeah. So maybe I'll, yeah, I'm willing to agree on that. So, but just the comment was that sometimes in random you will get things that are better than in general. Okay.
Okay.
Any other comments, complaints? Okay. Good. So, again, so the question is the algorithmic question. Can we find the intervals efficiently for a given input necklace? You have now this long necklace, random or non-random or looking random. So really it's a big necklace. We know that we can cut it, let's say just k equals 2 now. N types, we know that we can cut always in n places in a fair way. Can we find it? So that's an interesting question, and the answer is probably not. And what I mean by this is, so I'll talk a little bit about hardness and about approximation. So you know that in complexity theory in general, there are basically no lower bounds. So we don't know to prove any meaningful lower bounds for any interesting problem. But what we do instead is that we prove relative results. We prove that some problems are as hard as many other problems. And the formal way to say it is that some problems are complete for a certain appropriately defined complexity class. So Christos Papadimitriou defined several complexity classes that have to do with the complexity of finding a solution to problems that always have solutions. So these are problems in NP. Always there is a solution. Let me not be completely formal here. And then we want to find one. Okay, and two of his classes are called PPA and PPAD. PPA stands for polynomial parity argument, and the D is directed. So they are defined formally, and they contain several problems. PPAD is somehow better known because it contains some natural problems like finding a Nash equilibrium in a 2-person or 3K-person games. And there is a relatively recent result by Philostratsikas and Goldberg. And what it says is that for this necklace problem, K equals 2, the problem of finding these intervals for a given input necklace is PPA complete. Namely, and the other class PPAD is contained in PPA. So for example, if you can do this efficiently, then you can find Nash equilibrium efficiently. You can solve several other problems that we don't know to solve. So, so this is probably hard, or at least we don't know to do it, even if you allow a little bit more than n cuts. If you allow n plus n to the 1 minus epsilon, it's still a PPA complete. And this raises the question of what can we do efficiently, maybe with more cuts. So suppose we, instead of n cuts, we allow 2n or 4n or n log n, I don't know. We allow a little bit more cuts. Can we then do something efficiently? And there was some earlier result about that, actually back and late on, before the original Necklace theorem was proved, they actually asked about it, motivated by some question in VLSI circuit design. And they could prove something that was good enough for their need. So they could prove that for fixed, for any fixed epsilon, and now think about n is not so big as a function of the total length of the necklace, then they could cut it efficiently in something like 1 over epsilon to the n places. So it's much more than the n cuts that are needed. And then they would get an epsilon approximate halving. So not everybody will get exactly the number of bits that is supposed to, but you will get it up to epsilon. Everyone will get between half plus epsilon and half minus epsilon of the bits of each type. And there is a related result, but these guys care also about some different aspects of the algorithms we are allowed to use, so let's not worry about this. But you see, even here, if n is the number of types, if epsilon is fixed, and n is, I don't know, log the length of the necklace, then this is still a reasonable number that of cuts that we can do. And maybe we want to do better, so this is another result that I want to say something about, depending on how much time we have. And this is with Andre Grauer, who was a student in Princeton, now is in Stanford. And it says that the necklace having problems, so now we want to partition it exactly to 2 equal parts with bits of n type, and at most m bits, let's say, of each type. This can be solved efficiently doing something like n log m cuts. Okay, so we allow more cuts. And if we just want an epsilon approximate halving, so instead of the exponential behavior before, we would know, we could do it efficiently with n times log of 1 over epsilon number of cuts. So you see that if epsilon is a constant, then this is a linear number of cuts. As I said, even, so this philosopher Tsikas and Goldberg with Fredrickson and Zhang, they proved that even for fixed epsilon, and even if you allow n plus n to the 1 minus delta cuts, then it's PPAD complete. So it's hard in some complexity class to find these cuts. But what is written here is that if you allow a little bit more, but still a linear number of cuts in n, then you can do it efficiently. Okay, so this is what about the cycle and triangles? Let me tell you something about this. So again, repeating it, it says that when we have a graph on 3n vertices, whose edges are the union of a Hamilton cycle of length 3n and n pairwise vertices shown triangles, like the one you see here, then there is an independent set of size n containing 1 from each triangle, like the one you see the beginning of it here. And as I said, this was proved by Ryser and Stibitz. They use some polynomial methods that is based on some ideas of Mickey Tarsi and myself, and there are also topological proofs. one of them by Aroni, Holtzman, Howard, and Prussell, and another one in this multi-author paper that I mentioned. So there are algebraic proofs and there are topological proofs. None of them gives an efficient algorithm for finding this required independent set. And here actually also hardness is not known, but so I wrote it here. Given a graph G like this, 3n vertices, Hamilton cycle plus n vertex triangles, can we find efficiently the independent set? Well, a very recent result by Ishai Chaviv is a PPA hardness of the extension I mentioned with in the paper with Aroni, Berger, Chudnovsky, Kotlar, Lebel, and Ziv. So here is an extension that is mentioned here. This one here to find the independent set is also PPA complete. But somehow the proof does not work for the cycle and triangles. And maybe actually it's not so surprising that it does not work, because as I said, this cycle and triangles has at least two proofs, the algebraic one and the topological one. So showing that it is PPA hard or PPA complete would place PPA, the complexity class PPA, inside the complexity class that corresponds to this algebraic proof, say, some version of combinatorial Nullstellensatz or some version of some algebraic thing. And this we definitely don't know. So it will be somewhat strange if this topologically defined complexity class will be inside the algebraically defined complexity class. So in general, we always like to have different proofs for the same statement, and it's always nice, but actually it's not desirable if you want to prove hardness. It is harder to prove hardness if this is the case. Okay. But okay, so that one is.
Noga, can I make a quick ask a quick question about the previous result? What kind of cycle length does he use? Just out of
so it has to be long. So it has to be polynomial in n.
Okay.
Right. Yeah. We don't allow here more than polynomial in n. I mean, his input is right. Yeah, and still, but he needs polynomial in n. And actually, it's not so difficult. He basically can reduce it to the hardness that is known for the necklace problem. You can see that this is somewhat related. Okay. Now I want to say something about proofs, and kind of my plan is to prove one existence result and one algorithmic result, and both of them will be geometric proofs. So after all, this seminar, I think the official title is Combinatorics and Discrete Geometry. But it will be okay. So it will depend on the time. And if we don't have time to cover everything, I think it's still also fine. So still don't hesitate to stop me or to. Okay. So I want to give one example of the statements that I told you about nearly fair representation. And this will use a Kara-Theodori theorem. So now we don't worry about algorithms, although actually here everything will be constructive. Let's say. And I told you that this statement was pretty general, so I just chose here some representative example. Here is a representative theorem. So we color now the edges of the complete graph, Ka. Okay, you can do it for complete bipartite if you prefer, but I said it here for a complete graph. we color it in any way by any number of colors. So M colors and Fi edges of color I, where Fi and M are arbitrary. And what I want now is to find a nearly fair Hamilton cycle. Okay, so what would be a fair Hamilton cycle? A Hamilton cycle contains n edges. Out of the n, choose 2 edges of the complete graph. So we took a fraction of n over n choose 2, which is 2 over n minus 1. So if we have f sub I don't know, by the way, my mouse, can you see it when I'm using it?
We see it.
Yes. You see it, right, yeah. So if we have Fi edges of color I in the coloring, then the fair share of the Hamilton cycle would be 2 over n minus 1 times Fi. If things would have been completely ideal, then Gi would have been this. And what we want is that the difference in absolute value will be small. And the main thing that I want, or...
Noga, sorry, why over n minus 1?
Because it's n divided by n choose 2, right?
Right, sorry.
Right, yeah, so it's 2 over n minus 1. Good, and what we get here is some bound that depends only on the number of colors, right? So for a fixed number of colors, then this will be pretty good. So it means that each color appears roughly the right number of times. Of course, it would be nicer to get here a bound that is independent of the number of colors, and definitely the conjecture should be that such a bound should exist. But this is what I know, and this is what I'll try to prove. Okay, so this is a statement. Now here is a sketch of the proof. So I'll describe almost everything. At the end, there is some computation that I'll not show. So when we have a Hamilton cycle, then we represent by a vector of length m the number of edges of each color. So G1 are the number of edges of the cycle of length of color 1, color 2, and so on, up to color m. And F will be the fair shares that they should have gotten, namely 2 over n minus 1 times the number of edges of each color in the complete graph, right? So this what so what we want is that each Gi will be close to the corresponding Fi. In the vector F, we already normalized it there. So let's choose the Hamilton cycle, H star, I call it, among all the possible choices, so that it minimizes the L2 square norm of the difference. What we really care about is the L infinity norm of the difference, but somehow it's easier to control the L2 norm. So let's choose one for which this is minimum, and we want to show that this is small. This gives a bound for the L infinity norm as well. So what we do is that we consider all the Hamilton cycles H that can be obtained from H star by a single swap. What is a swap? We delete 2 edges and we add 2 edges and we keep it a Hamilton cycle. Here is an animation showing it. So we delete the 2 red edges and we replace them by the 2 dashed edges, and we get another Hamilton cycle. And we can do it in all the possible, maybe n times n minus 3 possible ways, I guess. Okay. Now for each edge E of Kn, we can define a vector which tells us basically the color of this edge. So it's a vector of length m, where the coordinates correspond to the colors, and it has one only in one coordinate, in coordinate j, where j is the color of this edge, and 0 everywhere else. And an easy observation is that if h is obtained from H star, by removing the edges E1, E2, and adding the edges E3, E4, then it's clear that the vector corresponding to the new Hamilton cycle H is, now I'm still only defining thing. So let's define V of H. It will be the change, the vector of E3 plus the vector of E4 minus the vector of E1 and E2. Namely, this is in general a vector with 2 plus 1s and 2 minus 1s, which could also be 1 plus 2 and 2 minus 1s, depending on the colors. But basically, it tells us which 2 colors we are adding and which 2 colors we are subtracting. And what I was saying is that it's obvious from the definition is that the G vector corresponding to the new cycle after the change is what we had for the old one plus V of H, right? V of H exactly does the difference. Okay. And then there is something to check here, and it is the following, that if we sum all the VHs over all the possible swaps, so over all the n times n minus 3 over 2 swaps, then what we get is some constant multiple. I'm actually not completely sure if this is n minus 1 or n minus 3, but it doesn't really matter. Maybe it's n minus 3 times the vector f minus the vector g of this champion or this best Hamilton cycles that we chose. Now you see, by symmetry, if we take the sum of all the VHs, then it's clear that every edge, let's look at this picture again, every edge that is not in the Hamilton cycle will be added the same number of times, and every edge that is in the Hamilton cycle will also be subtracted the same number of times. So this means that this sum should be some constant times f minus possibly some other constant times g, but the 2 constants have to be the same because the sum of the coordinates of v is 0, and so is the sum of the coordinates of f minus gh. So they are the same, and if you work it out, it's some constant, I think, n minus 3, but we don't care. So it's some positive constant times this. So it means that the vector f minus g is a positive linear combination of the vectors vh, but those are all small vectors of dimension, they are of length m. In fact, they live in dimension m minus 1 because the sum of coordinates is 0. So by Noga theorem for cones, f minus g actually is a linear combination with positive coefficients of not too many of the vectors vh, of only m minus 1 of them. Okay. And now, so here I didn't write the computation, but basically by Cramer's rule and Hadamard inequality, the coefficients are not too large. So you can bound the coefficients. And this will imply that VH, some VH will have big inner product with f minus g. Because f minus g is a positive linear combination of a small number of them with small coefficients, then some inner product will be large. And then it means that if I'm going to change the g to the new g, g plus h, then when I take the L2 norm square, then I gain something, right? Because I subtract the inner product of f with this v of h, which is a big thing, and I'll add only the inner product of vh with itself, which is small because this was just a vector of L2 norm square at most 8. But we know that, that this h star was the one that gave the optimum. So if we just work out the details, then it will imply that the L2 norm of of this difference is at most what is written here. And here I'm not showing the computation, which can be done. And this basically implies the same bound for the L infinity norm. So, so this is how it goes. And indeed, it gives a bound that deteriorates quickly with a number of colors. So that relates to the questions that Andre asked at the beginning. Once the number of colors here begins to be more than a logarithm of the size of the graph, then it stops being interesting, because even a random thing would be just as good. And you can see that not too much was special here for the Hamilton cycle, right? So what we used is that we have these swaps, so that for any fixed cycle, there are many ways to change it to another candidate by changing a small number of edges, and that these changes, they cover every edge that is not in the cycle the same number of times, and then the argument would work for different structures. So this is supposed to convince you that this is plausible, that if I change the Hamilton cycle to a perfect matching, and I change the complete graph to a complete bipartite graph, or I change the Hamilton cycle to a n/3 vertexes showing triangles, and stay in the complete graph. So this statement of the same form would still hold, and even for hypergraphs. Okay. So this is about that proof. And now I want to say something about the algorithms.
Okay, so a little question. So this bad constant comes from the estimating this, how big is the scalar product?
That's right, yeah. So it comes really from the determinant, from Cramer's rule and Hadamar's inequality. So somehow the coefficients may be big, maybe, yeah.
Okay.
Okay, and yeah, maybe there is a way to do it in a better way. Okay. Yeah, but still, the nice thing is that for a fixed number of colors, it's a constant that depends only on the number of colors. Now I want to say something about the algorithm. So what I'll try is to show you the proof. Yeah, maybe to show you the proof that for the necklace having problem. So we have an open necklace, an interval of beads of n type, at most m beads of each type. And we allow ourselves now, instead of n cuts, we allow n times log m plus 2, never mind, number of cuts. And we want to split it exactly evenly. We assume that the number of beads of each type is even. Okay. So here is what we do, and we want to do it efficiently, of course, right? That's the main thing. So first we move again to the continuous problem. So we replace each bead by a small interval of its color, as you see here. So we get this n probability measures corresponding to the beads of each type. There is a red type and the blue type, the yellow type and the light blue type here, and we normalize it so that each of them is a probability measure. And let's say that we place everything on 0, 1, just again for normalization. So we now have the interval 0, 1, and we have n probability measures on it. And for now, you can even, yeah, I mean, we can partly forget that the supports are disjoint or where these probability measures came from. But since we want to do everything efficiently, then we have to remember maybe that we can compute efficiently things here, right? That if, okay. So now we have for a given interval in 0, 1, let me denote by p sub 1 of I, p sub 2 of I, up to p sub n of I. This will be the measures, the corresponding measures of the interval. And I want to define a total measure. So P of I will be just the sum of the measures according to all the measures. So P of the whole thing is N, right? It's okay. And what we want to first do is to cut the interval 0, 1 into 2n intervals, each of total P measure, which is equal, namely equal to 1/2. And you realize that since the way the measures are done, it's obvious that we can do it efficiently, right? So we can really find an interval from the beginning whose measure is exactly 1/2 because it's simple, right? So we have this split into 2n intervals, each of total measure 1/2. And for each of these intervals, we let v of the interval j be the vector of the measure of it according to each of the n probability measures, right? So this is an interval. It sort of measures what fraction of the red beads it has and what fraction of the blue beads and so on. So we have these intervals. And what we really want to do is we want to generate a collection of not too many disjoint intervals, right? This is where we would cut, and then we would have these disjoint intervals. And the sum of their vectors, and these intervals will give it to thief number 1. So the sum of the vectors of these intervals, ideally we want it to be exactly 1/2, 1/2, 1/2, and so on. So what we want is that it will be within distance 1/m in the L infinity norm from the vector 1/2, 1/2, 1/2, and so on. Once we are within 1/n, then this is less than the measure of 1 bead, and then it is easy to see that we can actually round it and get a desired solution that is precise, right? I mean, the cuts here could possibly be in the middle of small intervals corresponding to beads, but there is always a way to shift them a little bit and to round them so that it will be okay. So we just need to find this collection. And the thing is that H, this vector of 1/2, 1/2, 1/2, 1/2, is exactly 1/2 times the sum of all the vectors. So we really have 1/2 the sum of vectors, and we want to be close to it by taking a sum of a subset. So these is really similar to things that people are doing in discrepancy theory. And we want indeed to do something similar, only there would be some variance, but it's definitely motivated by the methods used in discrepancy theory. So we would maintain an expression of H, of this H, as a linear combination of vectors, Vj, for disjoint interval j that will keep changing. And the coefficients will always be in 0, 1, in the full interval 0, 1. But when the coefficient is in the boundary, it's either 0 or 1, we will call it fixed and we will not change it anymore. And if it is in the open interval between 0 and 1, then we call it floating. This is the same kind of thing that is being done, for example, in the Beck-Fiala argument. Okay. Now, by standard linear algebra, so I wrote here basic solutions of linear programs or a linear algebra, this H that is a sum of 1/2 times all these 2n vectors, we can express it as a linear combination of the original 2n vectors, Vj, where at most n of the coefficients will be floating, and all the others will be in the boundary. So this is very simple and just linear algebra manipulations. We have to check also that everything is efficient. We only solve equations. As long as we have more than n floating coefficients, we find the linear dependence, and we add or subtract some constant times this linear dependent to make at least one of the floating coefficients fixed, and we keep doing it until we have at most n floating coefficients. Now, once we have such an expression with at most n floating coefficients, we look at each interval with a floating coefficient and we split it into 2 equal parts. So each of them will now have p measure, this total measure. Before it was 1/2. The measure now will be 1/4. We split it to 2 halves. And we keep the same floating coefficients for each of the halves. Okay. So now we increase the number of intervals, but still the sum, the linear combination that we have exactly gives us the vector 1/2, everything. And now we can shift the coefficients again until at most n of them are floating. And then again,
Noga, sorry. So here you don't keep the floating coefficients. You only start with floating coefficients that are the same. After that, they're not the same, right? For the 2 parts.
Right. So after that, they are not the same, but every pair will be the same, right? For a while. But it's true. So at the beginning, we started with everything being 1/2. After a while, we don't know what they are. So there are some numbers. And then we split each of them to 2, and we keep, so each coefficient appears twice now, but then we shift them again, and they move, and we don't have control on this, and both n of them are still floating, okay? And then still, we would take the floating ones, and we split the intervals into 2, and we keep doing it. And if we keep doing it log m times, then we will obtain an expression of H as a linear combination of at most n log m intervals again. And each p measure will be at most 1/m, and we'll have at most n floating coefficients. Right? So this is but now indeed the measure of the intervals with the floating coefficients is very small. Yeah, I think something here is a little bit inaccurate, but I wrote it. So each p measure of an interval with a floating coefficient is small. Some of the intervals with non-floating coefficients may have big measure, but we don't care about that, right? But the p measures of the interval with floating coefficients are small. And now from now on, we are not going to add cuts at all, but we will only keep changing the coefficients for a while. Okay, so no, the cuts are the n log m or so that we had so far, and okay. So let me describe the rest of the argument. So now the sum of the p measures of the intervals with floating coefficients is at most n/n, because we have at most n of them, and each one has a measure at most 1/m, and therefore there indeed exists some index I, one of our measures, so that the sum of pi measures of these intervals, the floating intervals, is at most 1/m, because there are n measures, and the p is the sum of all of them. So we can fix such I, and then we can forget about the coordinate I. Why we can forget about it? Because no matter how we will round the vectors now or shift the coefficients, then in this measure, we are already okay, because the sum of the floating, the sum of the measures of the intervals in which we are changing things according to the measure I is less than 1 over m. So it will not change by more than 1 over m. At the moment, it is exactly half, and when we will change it, it will be at most, it will deviate from 1/2 by at most 1 over m. So we can forget this coefficient. Once we forget it, we have vectors of length n minus 1, and therefore we can reduce the number of floating coefficients again to n minus 1, and then we can keep repeating it until at the end we are left with one vector of length 1 whose unique component is less than 1 over n, and we can include or not include in our connection based on the rounding that we want, and then we round the cuts that lie inside the bits. So basically that's the whole thing, and the thing to observe that it gives us the collection of disjoint intervals, so that's the sum of their vectors, which tells us how much of each measure we got, is very close to 1/2, 1/2, 1/2, and the number of cuts is correct, and the algorithm is efficient, because the only things that we have to do there is to compute p measures of some things and to solve systems of equations from time to time to find the linear dependence between floating coefficients and to use it to reduce the number of floating coefficients. Right? So this is about that. And the only thing I still want to do is to, unless there are any comments about this, so I only want to mention one problem. So there are several problems that I already mentioned, right? I mean, Ryser Conjecture, if you want, or to find an efficient solution for the cycle or triangle problem, or to prove that such a thing is not likely to exist. But let me just mention a conjecture about the existence results that I showed you. So the following, it looks that the following should be true, I think. So suppose you have an integer d, then there should be a constant depending only on d, so that for every m and every n, and every graph h on n vertices with maximum degree d. So this is what replaces now the Hamilton cycle. I want to get some copy of h, which is a graph with maximum degree d, possibly on all the vertices or on part of the vertices. And we have an edge coloring of the complete graph on n vertices by an arbitrary number m of colors, and it has fi edges of color I. Then what we want is to find a copy of h which contains gi edges of color I, and the fair value of gi should have been fi times the number of edges of h divided by the number of edges of the complete graph, right? So that would be the fair share of h. So ideally, gi should be equal or very close to this. And what should be true, I think, is that the absolute value of the difference for each of the colors should be at most some constant depending on the maximum degree d of the graph. It's easy to give examples where showing that indeed it should grow with the maximum degree of the graph, but as far as I know, it shouldn't grow with a number of colors, and it shouldn't grow with a number of vertices. And the proof I showed is that if we will allow this constant c of d to depend on the number of colors also, then this can be proved in many cases. Again, I don't know it for completely general graphs, but for lots of graphs and even for hypergraphs. But the main thing is to get rid of the dependence on the number of colors. And with this, I'll finish and thank you for your patience.
Thanks a lot, Noga, for your great talk. Questions?
In case of one of the initial problems about the matching in the complete bipartitive graph and the existence of a matching, is it possible to use such approach that I like thinking about matching at the integer vertex of the polytope that says that the polytope of fractional matchings. Is it possible to prove something about points that are in the linear combinations of not too many vertices?
Right. Yeah. So then, so this is very similar to the kind of thing I was describing. So if a point is inside the matching polytope and it's a linear combination of a small number of matchings, then you would expect. So I'm trying to think. Yeah, actually. So actually, I'm not. I mean, let me answer maybe. So I'm not. Yeah, I don't see it now, right? I'm not sure. You would. I mean, of course, the conjecture is that every point inside the matching polytope is, in some sense, close to what a vertex gives you, right? But this is what we want to prove, and you're asking if it's easier if this is a union of a small. It's not completely clear to me. Like a Hamilton cycle is just a union of two matchings, and it's not clear that if you have two matchings, one of them is completely red and the other is completely blue, why does it follow that there is a matching that is half red and half blue? I mean, here it's easy because for two colors it is easy, but it means that we have to move to some other vertices and not just the vertices that give the specific point. Right, the Hamilton cycle divided by 2 is a point in the matching polytope. And I'm saying that you would have to go to other vertices and not only to the vertices that the specific point is a linear combination of them. But still, maybe there is a way to do it. So, yeah, so I don't know if this answers, but.
Thank you.
Okay.
There is one question in the chat about.
Yeah, look at the chat. Okay. But yeah, but see, someone is asking about a group, so a group of swaps which act on Hamilton cycles and give rise to some nice groups. This is what I see in the chat. I mean, those swaps, they define some group, but this will be not such an interesting group. Maybe there are more interesting groups that could be grade groups or Coxeter groups. I'm only reading from the chat. I don't know. I mean, it might be that some of those swap.
Just a small question from me. So just to make sure I understand correctly. So this question that you ask here, Noga, it's even for the, so for the Hamiltonian cycle, we don't know the answer. And even for the matching,
We don't know.
This is what you showed in the beginning, rough.
Right, yeah, definitely. We don't know how to get a bounds. It does not increase with the number of colors. Yeah, that would be nice, I think. I mean,
but it does not. It does not include Ryser conjecture somehow. Does it include some?
Because we allow this C of D. So Ryser conjecture is really it's in a very specific case, but it wants that the error will be really less than 1, right? So it's very exact. Yeah, I mean, of course, one can ask about the best possible value of the error also, but that seems to be far from what we know.
Are there any results of this spirit for Ryser? Meaning that, okay, if we allow to use every color at most twice.
I'm pretty sure. I mean, definitely we know that there is a Latin transversal of size n minus polylog or something. And
yeah, log square, at least log squared, yeah.
That you have a Latin transversal or a matching, which is not perfect, but contains n minus log square and they are all distinct. And now you just have to add log square additional edges. And I'm not sure if this is written anywhere, but I'm sure that if you are allowed to use every color twice, then it's possible to get the matching always.
Okay.
So because it's yeah. So once the number of colors begins to be very, very big, and those are very small, then maybe it becomes easier again. Right. So it looks right.
Thanks a lot, Noga, for coming to Moscow and giving this talk.
Yeah. That was my easiest trip to Moscow so far.
Thank you very much.
Bye. Yeah.
Bye.
Thank you.